Hi, good morning. This is the continuation of lenses. In this video, I'm going to talk about how to draw the ray diagram for a diverging lens, and then show you how to do some of the calculations using diverging lenses. So a very quick recap, because I assume this is review from the previous video. Lenses take light and they actually bend them due to the fact that we have light coming in from one media source, which is in this case air, and then entering another media source such as glass. And when that happens, light slows down and bends towards the normal. So that's the whole premise of this. We're using Snell's law to kind of analyze these cases. So very similar to mirrors, we're going to apply these things called the rules, or the principal ray rules, to show us how to do the ray drawing. Now there are the three rules which are similar to the mirrors but a little different that I'm going to demonstrate. They're all written out in the slide, so that's why I'm not going to write them out right here, but I'll verbally go over them and show you how to analyze the image that's formed after you use the analysis. So just as a quick review, let me just grab my tablet here. All right, let's get this going, and let's do this. So just a quick note, this doesn't have to do with the thing right here, the object. I'm just going to show you something just as a principle. So this will be fine. So as a diverging lens, what happens is when you have the rays, they're going to actually literally go away from the object. So if I have this incoming ray straight, they're going to kind of do exactly what you might imagine, which is not come to a point, so they diverge. On this line, it will go straight through, but then on this line right here, this is what the rays would do more or less. So one big thing that comes from this concept is because these rays never come to a point, there will never be an image on this side. That's because the rays do not intersect, which is the premise for image formation. So, which means that, remember, by definition, this is the real side of the image. So all diverging lenses will make virtual. Which, in other words, if we were to continue these lines over here, I drew this very poorly, but actually, if I drew it more accurately, we would see they all come to some sort of focal point right here. So what I just demonstrated is kind of the method that we're going to do, is we're going to draw the incoming ray and the diverging ray, but we're going to take the diverging ray and continue it on the other side of the mirror to find out where it goes. So with that said, let's go ahead and do it. So I'm going to now do this with our principal rays. So there's three rules, although two actually work best here. The first rule is we start from the top and we go parallel to the principal axis. That's what I mean by parallel. Parallel to this big line right here. So what's going to happen is this thing will diverge. It will go out this way. But the angle at which it goes out has to pass through the focal point over here. So in other words, this is the diverging angle that it goes out. It passes through the focal point. That's the first rule. Now, I'm just going to continue this out as best as I can because we know the image is going to form over here, but where, we don't know, right? So, I'm sorry, I started at case 2. That's okay. You can start at case 1 later. Now, the other rule that works best is the following. So now I'm going to take my incident ray and go through the center of the lens, just like that. So, if we go through the center of the lens, the rule is that it hits it just at the right spot, so there's actually no diffraction. So it actually just continues out at the same angle like this. And I think that's the same angle. Doing it as best as I can. Here's the tricky part about this. This is really confusing, so I'm going to try to make it as clear as possible. So this is, remember, the diverging ray. These two rays will not make an image, so we need to go backwards. Now, it just is coincidence that the ray that went this way is the same ray that goes backwards. So what I'm going to do is draw it on top of it. But yes, this is really strange, and I know that even as I'm talking about it. But remember, we draw the ray backwards, so it does go on top of this line. So here's where we have two dotted lines meeting, and it just happens to also be in the same spot. So that can be confusing, but keep in mind that I'm not connecting these. I'm saying the image is here, not because there's a solid line and a dotted line, because I'm saying there's an image because we have two dotted lines right there. So that would be the person right here. Remember, the top of this mark is the top of this mark, and that's why I'm drawing it toward the principal axis like this. So according to our little setup here, notice that it's upright because it's the same side as the principal axis. If it was underneath, it would be inverted. This thing is reduced. Notice that it's smaller physically. This is, making up a height here. 5 feet, and this would be like 2.5 feet. So definitely smaller. And I know I can't really check on it, but this is virtual because it's in front of the lens. In fact, diverging lenses will always make upright, reduced, and I know you can't see it, but virtual images. Now, the third rule that we've done before says, if we go through the focal point, we'll go straight out. But the problem with that is that if we did that, it doesn't actually pass through the lens. I did a poor job of that. But point being is this line doesn't actually help us because we need to pass through for diffraction. So because of that, we're not going to use the second principal line, or the third, whatever the number is. We're just not going to use the fact that it goes through the focal point. So this is sufficient for our image. So actually, let's go to case 1 and do the same thing and watch how this works. So same kind of process here. I'm going to go ahead and start with my black line here and do the incident ray parallel, just like that. There we go. My refracted ray will go through the focal point, just like that. Oh my goodness. So I'm glad that I caught that. My refracted, common mistake. My refracted ray goes through the focal point, but it goes this way. There we go. That's what happens when you go too fast. That's better. Remember, diverging lenses sends them out like that. And I'll just continue the line like this. Okay, now let's do a new line. And say if we go through the center of the mirror, center of the lens, I notice I said mirror, it's going to refract at the same angle straight through, but I'm just going to follow this backwards. This is actually, I'll even do it like this to show you that. That is where we go. It's the top of the person right here, and there's my person. Same rules. Smaller. We look down here. It's upright, reduced, and virtual down here because we're in front of the lens. Okay, so then this is the best way to do this. You could use the other one, but it's definitely a lot more tricky, so I actually recommend just sticking to using this line here and this line here, and this will always give you the correct answer. So always true is that diverging lenses give you upright, reduced, virtual images. And as you saw from case 2, that was also true even in front of the focal point, so this always works out this way. Okay, let's get out of here. In the last part of the video, I'm just going to demonstrate some calculations. These are not, referencing the previous drawings, but we can show you how this works. So let's try A together. So we have a diverging lens that has that focal length. Now this is a really nice problem because it actually already made the focal length negative. The reason why it's negative is it's the way the equation knows that it's a diverging lens. So we throw in the negative sign when we're doing that. So this problem actually already did so. It says an object is placed 34.5 centimeters, determine the image. So that this is what it becomes. So we have negative 12.8 centimeters. The distance of the image is 34.5 centimeters. We need DI. So using the thin lens equation, if I do, I die, we can go ahead and plug these in. So I get 1 over negative 12.8 centimeters like this, and then 1 over 34.5 centimeters plus 1 over DI. So let's go ahead and calculate that out. I have my calculator here. Don't worry, I have a spare calculator as that one's batteries are dead. Alright, so let's see, we have negative 12.8, and then I'm going to do shift inverse, minus 34.5, shift inverse, and then I'm going to take the inverse of that answer. Beautiful. Okay, so I get negative 9.336, so let me write that down. Perfect. Now that's good because the negative sign in front of the DI means it's a virtual image, so that absolutely checks out. So let's just quickly verify with magnification that this worked out. So this is not part of the problem, but let's just check to make sure that it's upright and reduced. So if I do this magnification, okay, so it's negative DI over DO. So negative DI, so negative 9.336 for the distance of the image divided by the object. So let's go ahead and do that, divided by 34.5. We get positive 0.27. So positive means upright, less than 1 means reduced. So I hope you see that this follows the laws of diverging lenses. It's virtual, upright, and reduced. Pretty cool. All right, next question, part B. Determine the focal length of the diverging lens that produces an image that is that from the lens and when the object's that from the lens. Okay, so we're looking for F now. So it says the diverging lens produces an image of 12.9 centimeters. Now remember that this is going to make a virtual image, so we have to add in the negative sign. It's not included there. So notice that I added because this makes a virtual image. And in fact, spoilers, this should be a negative focal point because it's a diverging lens. So here we go. So if I do, I die. So 1 over F equals 1 over do, which is 32.4 centimeters, plus negative die, like that. Alrighty, so solving this out, 1 over F. So here we go. I like to use the inverse function on my calculator, so I'm going to do 32.4 inverse plus 12.9 negative shift inverse. So when I do that, I get negative 0.047. I'm purposely writing it out now. The negative is a good sign, like this. This is actually inverse centimeters. Now remember, I have to take the inverse of both sides to get f by itself. Sorry, I included the negative, but you get the idea. Anyway, point being is I'm going to take the inverse of that number, which I will do right now. Negative 21. Oh no. Let me go with my history. Hold on. That's my number. Oops. Sorry. I'm going to just redo my calculation really quickly. Just give me a quick sec. Negative 21.277 centimeters. Now, depending on what the question is asking, you can either leave the negative sign or you can omit it. Now, the negative just means it's a diverging lens, so it's not a bad thing that the negative is there. It just reaffirms what we know already, that this is a diverging lens. But I know sometimes Mastering Physics just wants the value. So if it says it wants the magnitude, then you just type in 21.277. But if they want, if they're looking for the negative sign, you can add that in. But that's good. It checks out that this is in fact negative like that. Okay. So this concludes all the lessons on lenses. Hopefully this lesson helped you with diverging lenses and drawing diverging lenses. The next lesson is going to be talking about the applications of these lessons for eye corrections. Have a good afternoon.